To call Agile, Lean, and Rugged the paper edition. Our other working title was Killing Trees for Knowledge, but we weren't sure of how that was going to run, so we settled for this. And we're going to go for a little bit of introductions right now. My name is Ines Sombra, and I'm a distributed systems engineer with a company called Fastly. We're a CDN, a content delivery network. So you come to us, you give us your data, we spread it around the world, and we make your application faster. But I'm not here today to talk about Fastly. I'm here to talk about this organization that I'm a part of that is called Papers We Love. Also, I speak really fast. Sometimes my use of language is languageful. So just bear with me. Adrian is going to tell me if I'm going super fast. You're going to be like, I think it's my cue to drink every time I'm going really fast. But Papers We Love, I don't know, how many of you know what Papers We Love is? Yeah, cool. So I assume that maybe you went to a meetup, yes? Yes, cool. All right, so Papers We Love, if you don't know, is a meetup that deals with bringing, like the goal of the group is trying to bring academic research closer to practitioners. So every month we pick a paper, somebody comes, presents it, and people that are interested in just expanding their knowledge about computer science research can come and then just hear it and have a shared experience and a shared introduction to concepts that may or may not have been familiar to them. For me, it started with a very dreaded American tradition called the yearly performance goals. So it was 2014, and I realized that after I graduated grad school, I stopped reading papers, and I decided that year to take my yearly performance goals seriously. So I was like, I'm going to read more papers. And it was January, and a few days after that I started writing my goals, I noticed that the group in New York City started a meetup called Papers We Love. And obviously I'm like, sold, I'll do this with social pressure. And San Francisco was the second meetup that it started. And by now I think we're the largest chapter. It was 1,112 yesterday, maybe to like, who knows how many we are right now. But I think that this group and this organization hit a nerve because a lot of people had an interest for this, and now we have over 24 chapters all over the world, and London is included, and I think they meet on this building, and I think I'm actually ruining their meetup because I'm here. So, yay. So now I give it up to Adrian.
Okay, good evening. So my name's Adrian. I will try and bring balance by speaking a little slower for you. Adrian should be easy to remember. I'm also in the VC game. I work with Accel partners. Thankfully, the other Adrian has proved that you can do that and still be technical, so I'm just going to follow in his path. You may know me from former CTO roles at SpringSource, VMware, Pivotal, etc. But really, the most relevant thing for tonight is actually a blog that I write, which is called The Morning Paper, which started just over a year ago. I began reading a CS paper every weekday. And actually from the 8th of October last year, I had to look it up. I've been writing up a review of that paper every day on this blog called The Morning Paper, which has been a really interesting journey to kind of just to sort of immerse in that and to start learning and discovering, etc. May seem like an odd thing for somebody in my position to be doing, but actually what I've really found is, it's so hard, I'm sure you find this too, to keep up with the immense pace of change, the volume of information that's published every day, just trying to understand all of that. So what do? How do you get a handle on it? Especially if you're in a situation where you need to rapidly assess and come to judgments and decisions about which way to go and what paths to take, in my case investments, maybe in some of your cases what technology to build on, etc. And I found out that actually along this journey there are two things that I got from papers that are really useful to me. And one of them is looking at the foundations. So really understanding some core basic principles that gives you a context in which to go and understand when you encounter something new. Well, does this line up with what I know about foundational principles? Here's a framework I can set it in and understand it. And then the second thing that I really try and enjoy is looking at the frontiers, trying to understand where things are going. And, so I found that papers have been very, very beneficial to me for those two reasons. And so a mix of foundations and frontiers. And that's what we've done tonight to structure the talk. It was a difficult brief. I think you've got to give us some slack. Adrian said, I want you to talk about academic papers and I want you to be entertaining, which is not the immediate pair you'd put together.
Yeah.
But we do have beers to help. So we've taken on board a challenge. We are going to, in the three conference themes, obviously which you now know very well, Agile, Lean, and Rugged, we've selected 2 papers in each category, one that we're calling foundational and one that we think is a little more on the frontiers, although it's somewhat arbitrary, but they're all papers that we like. And to get through this in the available time, we realize that we've therefore got about 5 minutes per paper, which is actually pretty tough. And so to keep us to that, Ines decided, wouldn't it be fun if we had a strict timer and a bell such that, and I get to go first typically, if we overrun the 5 minutes, we'll get cut off. So most importantly, drinks should be on time following this mechanism.
Yes.
So those are the rules, 5 minutes per paper, 1 foundation, 1 frontier. No cheating, no adjusting the clock along the way, no ringing the bell too early, thank you. Going to need all the minutes we can get. So with that, let's dive in. Shall we look at some papers?
All right.
So the first category we've picked on is Agile, so the Agile category.
Do you want to come over here?
Why don't I grab this? Come to the center, yeah. So
Okay.
we're going to start with a foundational paper in the Agile category. And one of the things that this is very off-putting. I learned that already. One of the things we've heard a lot today is that agility is all about embracing change and adapting to changing circumstances and being good at doing that. This is a paper that a very famous guy called David Parnass wrote in 1994. And I love this paper because honestly, he could have been giving this talk at this session today. And yet this is way before you could have sort of predicted many of the things that we're talking about. It's 1994. He also wrote the marvelous On the Criteria for Decomposing Systems into Modules, but we won't talk about that today. One of the things he says really early on here is that actually success, we have to get over this excitement about getting to the first working version. And we have to think about success as planning for a series of changes over the long haul. And that's when we really know that we're winning. Now, I don't know if you've ever had the experience of looking at a piece of existing software, perhaps with a little bit of disdain, thinking, I could write that so much better if I could just kind of rewrite it in the right language, with the right tools, using modern design principles. It would be great. And Parnass says this is a bit like looking at an 86-year-old man and saying, he really should have had more exercise when he was younger, and not appreciating that the guy was actually a champion swimmer right into his 50s. And so, one of the points here is that what he calls software aging is just inevitable. What causes software aging? 2 reasons, Parnass says. The first reason is your software can become obsolete by failing to change. If you just leave it static, it doesn't adapt and keep up. A failure to change will age your software. It's obsolete. It falls off the path. The second reason that software ages is changing it. So you're damned if you do, and you're damned if you don't. Parnass says that if you want to plan for success, you need to plan for change. Because the only systems that don't get changed are those that are so bad that nobody wants to use them. Likewise, therefore, a failure to plan for change is really planning for premature aging and death, which I hope we don't want for our software. How does this aging happen? You hope that the original writer of the software has a clear concept in mind when they create it, that it's somehow conceptually integral and coherent. But later along, somebody comes along to do some maintenance to make a change, and they don't quite understand that clear original concept, and so what they do isn't quite in line with it. Now, to understand the software, you have to understand the original concept and the change that was made. Repeat this process a few times, and you find that the original designer of the software no longer understands what it does. The maintainers of the software never understood what it did, and therefore, nobody understands what this software does. Interesting. Now, software aging, he says, is inevitable. And as it happens, it reduces our agility. As software ages and becomes more brittle and harder to understand, the rate of change slows down. Also, the performance of the software may slow down as the structure deteriorates, and it tends to get more buggy. One of the reasons is weight gain. The easiest way, he says, to add a new feature to the software is to add new code. And we tend to violate the dry principle. We get duplication, etc. Now changes have to be made in multiple cases. We're on the slippery slope. What can we do? You're hiding the timer. What can we do about this? Preventative medicine. Parnass says, first of all, we have to design for change. Planning for change, remember, is planning for success. So think about that right up front. What can help with this? Embracing modularity and information hiding. In other words, breaking your system down into smaller, well-designed, coherent pieces that become units of change, which is kind of very reminiscent of microservices when you think about it. He also stresses clarity and documentation, maybe more so than we would today, but with the goal that, remember, you're writing this for the long haul. Think about the people to follow and maybe your future self. If a part of the software is too bad, just chop it off. Amputate the disease-ridden parts. Don't let it spread. Again, that means that having a unit of change you can easily amputate is great. And finally, plan for eventual replacement. It will happen. Software does age. Start saving financially and investing in new tools and techniques to be ready when that time comes. Look at that. Time out.
Yeah. Ooh, nice. First one. Okay. So we started, no, hey, that's a little
I've
too,
started.
okay, fine. This is like a little bit too soon. All right, so the paper that I chose is much better to hold the time over there. It's like every second counts. So this is fast database restart at Facebook, and then we chose this as an Agile paper that is in a frontier. So when we want, like as developers, we want agility of operation, agility of development, agility of testing and verification, and agility of delivery. But all of this deals with how we construct software and how we put it out in production. But once it's out in the wild, we actually need to support it and we need to do maintenance to it. So we also really want agility of operations as well. So people are dropping their drinks, woo. So this paper deals with Facebook Scuba. And if you're not familiar with Scuba, Scuba is an in-memory database that is used to monitor and analyze Facebook products and services. And the paper describes the struggles that the Scuba team was dealing with. So it deals with a little bit of the architecture, but we're not going to cover it all. I'm just going to tell you that there are machines, and each machine has some servers. And since it's in memory, all of the data lives in the server's heap. So this is all you need to know about Scuba. But the problem that the team was having, and the problem that pretty much everybody that has to deal with state at large quantities has, is that it's kind of tricky. It's not necessarily trivial. And for them, restarting a database cleared its memory. So it meant that they had to load it up from disk, and it was around 120 gigs of RAM from disk, and it took them around 3 hours per server, and you had around 8 servers per machine. So they did this strategy to actually get a little bit more functionality while they had to do an upgrade. And they did things like orchestrated restarts. Like they only restarted 2% of the fleet, 2% of the servers of the fleet. And they also, like, while servers were restarting, they used this thing that would be like they used a strategy called partial queries. So they don't return the full result set, but return a little bit, and then they keep restarting machines. But that thing took them around 12 hours and required a full-time engineer to actually monitor the process. And I don't know if you monitor the process, this is like how you look like whenever you have to do this thing. What the team noticed is that whenever they shut down a service for a planned upgrade, the server memory was in a good state. As opposed to whenever server crashed, and you can't really tell if the memory was good or not, if there was some corruption. So they decided to decouple the memory's lifetime from the process lifetimes. So they did it this way, and they did it by actually just like serializing and deserializing this data structures that went to disk. So it went from heap to memory, and then from heap to share memory, and then share memory was the thing that kept the state. Then the process restarted, and then it just read everything back from share memory into heap. And they used different data structures, and the paper covers this. And this is kind of like the description of how they did the staggered restarts. And it took them around an hour to do the full fleet. And the server took going from 3 hours, it took them around 2-3 minutes per server. So this is agility of operations. And this is what you look like if you're the engineer that is on call for that one. Boom. Yes. So, all right. Now we're going to go for lean.
Wow.
So far, we've done so good. Yeah.
Can I have your spare minutes?
No.
Oh, come on.
No rollovers. Yes.
All right, so a paper tour of lean. And I get to do the foundational paper again. Oh, you started the timer. OK, so my choice is scalability, but at what cost? It's actually a 2015 paper, Frank McSherry and et al. But I really like it. It teaches a very foundational, and perhaps you'll find it counterintuitive lesson when you first encounter it. And so it's teaching us to question why we're pursuing certain goals, and whether they are indeed the right ones, and whether they have lean consequences. So let's take a look at this particular chart, which shows here it's scaling out some distributed systems. So we're adding nodes, and therefore we're adding cores. And we're looking at the speed up that we achieve as we add cores. So this is a classic kind of scalability of my system show-off graph. And we'll see that system B starts to struggle after about 10 cores, and it sort of seems to be flatlining and not scaling terribly well. Whereas system A, as we add our nodes and add our cores, seems to scale quite nicely. Within the time limit, a quick show of hands, who would prefer to deploy system A? And who would like to deploy system B? One curious taker, because he's figured out there must be a catch. Here's another graph of the same system running the exact same workload. Again, we're seeing the number of nodes in our distributed system and hence cores. But now we're looking at the actual time it takes to process this workload. What I want you to notice is that system B, the system that scales the worst, actually performs better than system A at every scale. Now which system do you want to deploy in your data? System A or system B? That's kind of interesting, isn't it? It hurts. Hang on, I want to deliberately deploy the system that scales worse. That kind of we're so used to kind of scalability as a goal in its own right. Does your system scale its web scale? Single-minded pursuit of scalability, this paper shows us, could be the wrong goal. It's a very thought-provoking counterexample. We're more interested perhaps in performance at different scales or in cost performance, etc. How does this happen? So the common wisdom, as embodied in many, many papers and discussions and debates, is that if your system scales really well, you must be a really good system builder, because scaling is hard, and you've clearly done a great job. And McSherry et al. So actually there's some uncommon wisdom here. Any system can actually scale arbitrarily well, thinking about particularly distributed systems, with a sufficient lack of care in its implementation. How does this happen? Well, in order to get scaling and to go up to 300 nodes, we introduce all sorts of overheads and inefficiencies that are going to let us work in this distributed manner. They turn out to be easily parallelizable. Now you get a lovely looking scaling graph, but you don't have good performance. The second thing that tends to happen is that a programming model optimized around some of these distributed programming paradigms restricts your algorithm choice, and so you can't always encode the algorithm in the most efficient way. So they introduce the notion of cost. What's the configuration that outperforms a single thread? So the cost of a system is the number of hardware cores you need to use before your particularly distributed system implementation outperforms a competent single-threaded, single-core system. Many systems, it turns out, actually have unbounded costs. They never achieve this goal. So it's kind of damning and interesting. Let's have a look. This is graph processing. You do it in many other areas. 20 PageRank iterations, Google's PageRank algorithm, etc. Here's my single-threaded system on the top. So the parentheses, that's how many cores we're using. So you can see that most of these systems never get to beat my single core. So Spark with 128 cores, for example, is actually slower than my single thread on a single core. GraphLab, is it GraphLab? Just about does it, but it uses 128 cores to do it. 128 times more expensive than if you'd used a single core. Paul Barham said, you can have a second computer when you've shown you know how to use the first one. Choosing a good algorithm is really at the heart of computer science, and if we're forced into positions where we can't do that, it has serious implications for being lean. In his blog that accompanies the paper, Frank McSherry says, look, here's the acid test. If you're building a system for others to use, particularly a distributed system, just make sure it runs better than it does on your laptop. And by the way, he shows how you can do this with very large data sets and all kinds of things, so it's not just for small data. And if you're using some kind of distributed system, just make sure it's better than your laptop. So incredible implications for running lean here, just by kind of assuming scalability, following the crowd, and actually accepting a lot of inefficiency as a result.
We're doing so good. Yeah.
OK. I'm up next as well. I'm going to steal a few seconds from the reset. I'm going to do the Frontier paper. So Frontier paper, also from 2015, again thinking about lean. My choice is Approx Hadoop, bringing approximations to MapReduce frameworks. Now, whereas scalability, but at what cost, teaches us to question whether we're pursuing the right goal, this paper really teaches us to make sure that we're not asking too much of our systems. And again, I want to tease you with a graph. This time we're looking at analysis of the size of articles in Wikipedia. Okay, and so you've got page size in bytes and the number of articles that have that size. The green, the solid line, shows the absolute precise perfect results, analyzing every single article, looking at its exact length, and giving you this distribution. What's really interesting are the crosses overlaid. They're in red if you're not red-green colorblind. That's the same thing, but calculated by only sampling 1% of the data. So this was produced to say, look, within a 1% error bounds at 95% confidence interval, can you tell me what this distribution looks like? It turns out, if you're happy to take the red crosses rather than the solid line, again, you sample about 1% of the data, you can get that about 32 times faster, or using about a 32th of the resources. And I want to ask you, what do you really need? If your goal is to understand the shape of the distribution, to look at reports, etc., you're not doing kind of billing kind of stuff off the back of this. In many cases, is the red cross perfectly good enough? Now a report that you only ran once a month, you can run it every day for the same cost. Okay? There's a related piece of work, it's not in the paper, but I wanted to touch on it, called BlinkDB, which also incorporates this approximate querying idea. Now here again, we're seeing the cost of running a query against two different data sets, 2.5 terabytes, 7.5 terabytes, so big data. Query response on the y-axis. Note that it's a log scale, okay? And again, we're saying if we answer this query at 1% error, then at 2.5 terabytes, we're between about 10 to 100 times faster or cheaper. And at 7.5 terabytes, you're about 1,000 times faster / cheaper if you're prepared to accept that approximation, which I just showed you for many purposes is actually pretty darn good. How does the prox Hadoop actually work? And so it's a two-stage sampling process. What it does is first is it just chooses to input a subset of the data blocks. And then given that, it chooses to run or to drop a subset of the map tasks. Of course, the trick is figuring out how much data you need to look at and how many tasks you can drop. But after doing this two-stage sampling, to use it as an end user is dead straightforward. They provide superclasses for mapper and reducer that you just extend like you would the normal kind of superclasses. And that's it. Off you go. There are two ways of specifying what you want. You can say, if you understand your data set, this is the sampling rate I'm prepared to accept, and this is the drop rate for map-reduced tasks. Or you can tell it, this is the error bounds that I'm interested in, and this is the confidence interval I need. Now, error bound is how close to the true answer do I need to be? Within 1%, within 5%, within 10%? Confidence interval, how long do I have? Oh, perfectly timed. Confidence interval is how sure are you that you're within that error bounds. So for example, if I say 95% confident, 1% error bounds, that means 19 times out of 20, the answer I give you is going to be within that bound. How do they work out how much to drop based on this? That's kind of where the smarts are. That's the bit you wouldn't want to do yourself. So for aggregate computations, things that are doing, for example, a sum or a count or that kind of thing, they use multi-stage sampling theory. And if you've got a process that's looking at extremes, like computing a min or a max, etc., then the authors use extreme value theory and something called the Fisher-Tippett-Gnudenko theorem. Don't ask me about that, I can't tell you, but some smart guys have figured it all out. And really the takeaway for this for me is, don't ask wasteful questions. Do you really need the answer? Because getting from 99% to 100%, you pay a heavy price. Okay, go.
Okay, so now we're going to do rugged. At the beginning, we decided to split them, and then we're going to see if each one of us can take a full section. But it looks like we're made of time, so let's do it. So the first paper that is foundational that we've selected was Harvesting Yield and Scalable Tolerant Services. And the reason that we love this paper is that it was made in 1999, but a lot of the mechanisms and a lot of the strategies that you've seen us talked about in previous sections are actually like formalized in this paper, and it's really, really cool. So if this is my interpretation of ruggedness, which has nothing to do with security, so I'm sorry to the speakers. I really enjoy your talks and learn a lot of them. But yeah, it's true. I am dealing with like PCI right now, so it was like, so good. So ruggedness, I also, as a practitioner, when I think about ruggedness, I also think about system availability. And this is why I like this paper a lot, because this paper gave us strategies to enhance ruggedness in the presence of failures. So if you have anything that runs on the internet, eventually will fail, like it will fail. So the way that this paper actually gives us a mechanism and a better way to think about what do you do or how your system availability is impacted by failure. So that's why I like it, and that's why I put the knowledgeable Colyer. So the two concepts that this paper introduced is yield and harvest. So yield is defined as a fraction of answer queries, and harvest is a fraction of the complete result. So we now, like the authors propose that we start thinking about our system availability in terms of yield and harvest. And our systems eventually like have a preference for what they're going to be tolerant to. Are you going to be like favor yield, or are they going to favor harvest? And that is not something that you build after your system gets constructed. You build it. This behavior is an outcome of your system's design, which is something like really like pretty interesting. It's like you can't really build security X and after your system is finished, but it's the same thing with the behavior of your system in terms of failures. So these two concepts are rather tricky, so I'm going to cover them again to make sure that we understand them together. It took me a little bit of time to actually get what they meant by yield. So yield is kind of closer to uptime. They mean the percent of requests that get answered successfully, but it's more useful than uptime as a metric because it's correlated or it maps directly to user experience. So say, for example, you have a shopping cart and your system is a shopping cart and you're during Christmas season and then you have 2 minutes of downtime. That is a different yield than if your system goes down at 3 a.m. on a regular Wednesday, but it's the same uptime metric. So this is the interesting part. Then the authors tells us that we should actually be focusing on yield rather than uptime when we're trying to talk about our system's behavior. So harvest right now, this is a very illustrative example. So harvest is defined as the percent of the data that is included in the response from all of the data that we have. So say that I have this following distribution of data on servers, and I have cute on server A, baby on server B, animals on server C, and I want to search for cute baby animals. This is what happens when server B goes down. I have 67% of harvest. But actually, my query is pretty good. So this is, again, to like the approximation that Adrian was talking about. Like, we don't have to have 100% harvest to actually return sensible results. So the authors propose two strategies to help us build our systems in ways that are much more tolerant or rugged to failure. So one that they mentioned, like strategy number one, or door number one, is probabilistic availability. And this is where like the concept of like graceful degradation like comes up. So it's graceful harvest degradation because it's like graceful like ability to have like more like approximate result, and the guys on the scuba paper did that under a fault. Randomness is, for example, if I spread 1% of my data through different servers, then if one server dies, it's kind of like RAID, but for your saving of state. If one of the servers dies, then you actually have 1% that is randomly distributed data. You can actually replicate more things that are more important to you, and you degrade result based on client capability. And the second one is decomposition and orthogonality. And decomposition, the only thing that is really important that I want you to take away from this is that you can split your application into subsystems that are independently intolerant to failure, but your application itself is like tolerant to those systems' failure. So it's kind of like you build an API tier, but everything under your API could fail, and you're okay. I have 28 seconds. And another thing that is interesting is that you don't have to have the same consistency for everything, only for the subsystems that need it. Orthogonality, you're going to have to go and read it on your own. Yes.
Hey.
Okay.
Well done.
Good. The next paper is a frontier paper. You can, yes, fine. And then this is one of the authors. We really like this paper. And again, I'm going to redefine the theme of ruggedness. And also, when I think about ruggedness, I think about our systems' like ability to stay up, as systems' ability to be secure. But the only way that you know this is actually via verification and via testing. And in the realm of testing, there's like all sorts of classifications, and this is my mental model. So you have things that are like much more academic, like formal methods, and then in formal methods you have things like human-assisted proofs, model check-in, like we're formal methods, and they're all great, and they give you this level of assurance that regular testing doesn't give you. But they're very, very labor intensive, and they also have very, very specific applications. So if you have something that is safety critical, you tend to go for a human-assisted proof. You spend maybe like 6 months of your life proving like 30 lines of code, but you really have like very, very great assurances. AWS is actually using formal methods, and they have a paper about it that is really, really interesting about how they use TLA Plus to verify and make more aggressive changes to AWS services. Then you have your regular testing, which is a thing that all of us do, hopefully, pay attention to your tests. And people classify testing depending on like the perspective on your system. So you have things like top-down, and you think like white black box is like awareness, but the paper introduces a new term that they call bottom-up. And they call it lineage-driven fault injectors are part of bottom-up. So I thought that this was the sound for this because like, yeah, it's really difficult to pronounce. So I'm not gonna say lineage-driven fault injectors anymore. I'm gonna call it MOLI because that is the name of the system that they implemented to prove this concept. And this concept comes from like database literature where they trace like the outcome of something, but then they use this mechanism to actually like seek failures. So MOLI reasons backward from a correct observed system behavior, and it tries to just like figure out what could have prevented it from happening, and that is super powerful. And then it uses this information to only put failures that it thinks could have prevented the good outcome from happening. So it's smarter than your regular fault injectors because it actually knows and has an understanding of how your application works. So say I want to build a rugged system with MOLI, and in the paper they describe the situation that it's kind of akin like a game with a developer and a programmer. I put a monkey, but no, nothing. Don't take any conclusions from that one. And the verifier is MOLI. So me as a programmer, I give MOLI my program, a correctness specification, my inputs, and a failure model. Like we have to agree on what are the failures that my application is supposed to tolerate and how many of them and over what amount of time. And MOLI runs my program and observes its execution, and then it's gonna pick a fault and from the things that we've agreed upon, and then it's gonna run my program again with that fault in mind. And we both get to observe the results. So if MOLI breaks my program, and the correctness specification is violated, then I lose, but I get to submit my program with a patch yet again. But if it looks good, then MOLI would, I win that round, and MOLI would pick another failure that is possible for my application, and then we try again, and we try again. And if MOLI breaks my program, then I lose. If my program like manages to survive this evaluation, then I win. And then I get a certainty that I wouldn't necessarily get with other fault injection mechanisms. Another thing that is interesting, that is like, why is this relevant, is because at the end of the day, formal methods allow you to have an analysis of all of the states that your program or your system can get into. But in testing, you actually have to force a system to fail. Otherwise, you have no confidence that it's going to operate correctly in failure modes. MOLI provides, as part of this execution, a way to help me reason about failure. So because after the first one, for example, my program was crap and it told me, and then that is a lineage thing, and then it gives me also a lineage cost and then a Lamport diagram so I can reason about time, then I get to submit it again, and by the end of the day, you see that my lineage is a little bit much more complex, and it's a little bit like much more sturdy. So you can see this in the paper. 50 seconds now. This is like actually not that bad, right? Yeah, we're doing good. So the reason that we like MOLI a lot is also because it presents a middle ground between things that are like much more pragmatic, like testing, and the formalism and rigidity of formal methods. I don't know if any of you saw those in school, but the first time I saw them, it was just like, ugh. And then I didn't understand why they were good, and then now I get that the certainties are much more they're much more concrete. They're mathematically provable. So like this gives us a middle ground, and it's dictated by the importance of verifying verifying fault tolerance in spite of the complexity of the space of faults. Okay.
No, that was a fake ring. You got.
And that is the hard part.
Seconds.
Yes. So the hard part is to know like what everything that could be in the like space of inputs. Yes. Woo.
Hey, well done.
All right. So hopefully by this time, what we're trying to do is like expose you to ideas that were new to us, or things that we actually like learn, and different perspectives that we acquire by reading papers. So even ourselves, like as we were toying with which paper we were going to put on different sections, we actually learned that our point of views were a little bit different, and then what I found valuable about one paper were the things that you found maybe and then what you found value were the things that I'm like, whatever, everybody knows that. But it's interesting. So what we did for you, in case you were asleep, I like to do this thing with my presentations where we put summaries, but I do call them TLDRs. So Adrian is going to take our first one.
Brilliant, thank you. So we looked at 3 foundational papers, one in each category, Agile, Lean, and Rugged. In the Agile paper, remember we heard from David Parnass, telegraphing to us from 21 years ago, designing for change is designing for success. So that's a really important lesson, and we've heard a lot about that today. In the Lean category, we looked at scalability, but at what cost? Frank McSherry, 2015. A scalable system may not necessarily be a lean system. And so just pursuing scalability for its own right out of some context may actually be quite costly. And the marvelous cost metric to help us evaluate that. In the rugged section, it is took us through thinking about availability in terms of yield and in terms of harvest, and the ability of a system to gracefully degrade and to still keep performing in some manner, even in the face of stress. And that's a great design outcome.
Oh, okay, mine again. All right, so in the frontiers section, we saw that when it comes to Agile, handling state can be challenging if you have to operate a database at scale, like you know this. And saving state and share memory, this trick that other people that were using even on Facebook, but this team leverage, allowed them to restart DB processes faster, and the team itself became more agile because in terms of operations, they were able to do everything that took them 12 hours in the span of 1. So that is super powerful. In terms of lean, asking the wrong question is wasteful, and you should think about what is truly needed. If you can use an approximation, then you save a lot of effort and a lot of work, and then actually like your process is much leaner because you waste less things. And in the case of rugged, then reasoning about from a good state and reasoning about backwards can just actually like help you determine if the execution failures that could have prevented this output from happening. So this is also very nice because like normally we're used to thinking one way, but we don't really think the way back. And I think this type of thinking also like helps us become a little bit more rugged because it gave us tools to actually understand what our systems were doing when they were being run. And yeah, so that is my rugged summary. We have compiled, so obviously papers are fun, read them. Sometimes it's a little bit challenging to get started into reading. But Adrian's blog is great because it helps you at least understand the gist of what you're reading. And we have a repo with everything that has to do with everything that we found helpful to actually get started with papers. We have linked to all of the papers that we've discussed. It's kind of a disservice because they're very, very good, and we had to distill them in 5 minutes. And there's much more information that is super valuable. So go check out the repo. There's linked to the slides already. I've already published them. And this is a reminder to actually join your local Papers for Love. If you want to speak, it's really great. We're always looking for new speakers. You don't even have to prepare a full-length talk. You can do a smaller one, and the organizers help you develop it. And the morning paper is great. So read it. And for now, we have like drinks. So, woo.